Hydrogen bonds, like I think we attached a bit on this slide last time, that they form when hydrogen atom covalently bonded to one electronegative atom, which is also attracted to another electronegative atom. And this happens in living cells because the electronegative partners are usually in the form of oxygen or in nitrogen atoms. So this kind of formations, or rather, what am I trying to say? These types of terms, you might also have to look for it. Starting from next week, we'll be going through your past question papers and past assignment papers. So when I was browsing through them, I saw most of the terms where your examiner might try to find out from you, what do you know about hydrogen bond. He can either ask you that in the form of a multi-choice question, or one word. Multi-choice questions don't always come in the form of choose, but it can come on in the form of giving a specific term, and also when he have given you multiple terms, and then you're gonna have to choose which one best to describe the terminology or the sentence topic which he had outlined. So you have to, especially here, because he has in your notes highlighted in bold some important terms which he can potentially ask you in your exam, or in your assignments. So hydrogen bonds, you need to know that they form when hydrogen atom is covalently bonded to one electronegative atom, and it is also attracted to another negative atom. So when we go forward, this is just the figure about water, which is the symbol, or the only thing that you need to worry more about here is just a structural formation and some form of description to symbols. That's one thing that you have to worry about. You don't need to worry much more about the description of a structure or the drawing of a structure in the form of these bonds. But remember last week we talked about, or we show you structures of how they form the bonds. So, but in the form of this, you just have to worry more about which bonds they are talking about, because if you look here, they are saying their forms, they form when they are covalently bonded. Remember, we talked about what is covalently bonded even last week. You can just browse in your notes that we did previously. Then then is bonded to one electronegative atom, which is also attracted to one another electronegative atom. So if you look here on the water, which is covalently bonded to ammonia, you can check that ammonia is electronegative charge also here with the charge here, or the comments are distracting me here. Let me close here. Thank you. Then this is a hydrogen bond which is occurring between water and ammonia as an example. So this is what we also touch a bit about this. There's also what they call a van der Waals attraction or interactions. You need to also make sure that in your studies, or when you're studying, you importantly know what these are. So you need to highlight them and make sure that when you get into your exam room, you don't get into your exam room blindsided without knowing what these are, these van der Waals interaction, because they are electrons that are not evenly distributed. So they may accumulate by chance in one part of the molecules. But this attraction occurs between molecules that are close together as a result of those charges. But the main point, and here's my PDF opening now. So the main point here on this is that these ones, when they occur or when they are distributed, they don't get distributed evenly. So you in these equations, you won't have to balance the equations. So the equation of this interaction of the van der Waal interaction, it doesn't have to be balanced. Why am I saying this? So your examiner might not necessarily say it when he's describing the van der Waals interaction. He might not even necessarily saying that the electrons are evenly distributed if he's trying to get a description out of you. He might as well just say uh, the interaction where their reactions or their equation don't necessarily have to be balanced. So you're gonna have to understand and know that he's talking about van der Waals interactions. And collectively, such interaction can be strong as between molecules of gecko store has and a wall surface. That's just a example. So if he can request you to also give an example of so he might say describe what van der Waals interactions are in terms of description. You're going to have to define them as the electrons that are not evenly distributed, and they are accumulated by chance in one part of the molecule. And also, if he said also describe also an example on top of that, then you will have to. But okay, there's still the comments from the students, from student numbers. You might have to also give the example that collectively such interaction can be strong, as well as between the molecules of a gecko, the gecko's hair and wall surface between those tores of hair. So this can as well be already a six marks question. Let me please just indulge with me when I go to the comments, or I could go to comments from here. I see there is a comment which is addressed to me here. Not about.
I think that one applies more to me. The recording students are currently being edited by our ICT department. I will then make the links. I think the first two classes are available. It is on YouTube, so I will then put the links for it in the chat box for our next class. Because what happens is they've edited it. They will then, during the course of this week, they will post it to YouTube, and it is then available. What you can also do is access it through your my UNISA, through the website. You will see the recordings, and you can then go there. But I will then give you specifically the link on how to access those recordings. Should it be available early this week, I do have your student numbers, so I will send you an email of how you can access those recordings. All right.
Noted.
That answers that question.
Hopefully the student is clear on that one. Thank you.
Thank you.
When it comes to molecular shape and their function, so the size and shapes are the key. Remember when we talk about we talk also about the talking about the phenotype or morphology, where I said it's about the description of what we can see with our eyes. And talking about size and shape, which are key to functions. So molecular shape is determined by the positions of atoms orbitals. So in a covalent bond, we talk about the covalent bond. There are what we call the s and the p orbitals, which may be hybridized and they create the specific shapes of these bonds on this molecular size. So this size and shapes, they are formed, or they are comprised, or they are built up from the covalent bonds, which are in the form of s and peace orbital, hybridizing those specific molecular shapes. So for those to work or to be visible, you can see here these are four hybrid orbitals. So these are the structure here of a molecule, where it's the s orbital, and here you can just, but you don't need to worry more about the description or the utilization or the outlining of these structures per se. But what you need to worry more is that the description and knowing exactly what these structures are, and knowing exactly what this description, especially in terms of highlighting of of these molecules and orbitals, because your examiner might actually just bring up the shapes, molecular shapes, and then you might have to describe which one represents the best term which he had given you as an option there. Where if you check here on the water type and the space filling model and the ball and stick model, which is unbounded on electron pairs here for the hydrogen. We'll talk also, you can see the covalent bonds there, and you see here some positive charges here, and then you see the description of this formation of CH4 is methane, H2O is water. Those are the kind of descriptions and the things that you might actually need to be able to make sure that you don't get into exam or to without knowing them. And you might also have to look out for that in your assignment and in your test. Here is the hybridization of this orbital. It's the same structure as this previously. It's just that this here is zoomed out, where you can have to see the s orbital, which is 3p orbitals. For hybrid orbitals of this structure is a tetrahedron. And as we proceed, you can see the space filling model, ball stack model, and hybrid orbital model with a ball and stick model, which is superimposed. And you can see that those pairs are unbonded. And there's also methane and water there, which they are unbonded per se when they are describing the. Like I said, you don't need to worry much more about the structure. What you need to just be sure of is the description and knowing that this is a molecular shaped form structure, and the previous one is the one for the hybridization of orbital, or just simply orbitals. And molecular shapes, what they do or their function is that they determine how biological molecules recognize and respond to one another. And these orbitates, such as morphine, and they naturally produce endorphins, which have similar effects because their shapes are similar, and they bind the same receptors in the brain. So this may actually be a question where you might have to describe what is the function, or what do molecular shapes do in terms of these orbitals, in terms of these molecules, that they recognize and respond to. They determine how these biological molecules recognize and respond to one another. And you may reiterate further, or you may indulge further by describing that example of morphine, which naturally produce endorphins and have similar effects because their shapes are similar and they bind the same receptors in the brain. So here is the receptors, where you can find that there is a natural endorphin when carbon, hydrogen, nitrogen, sulfur, oxygen, and morphine. And the first structure here, you can see that the structure of the endorphin and the morphine, what you can see here comparing to this. There's a natural endorphin and the morphine and the endorphin receptors. So these are just the binding endorphins receptors compared to the structures of the endorphin and the morphine structure. But also in terms of this one, you don't need no more. You don't need to worry more about the drawing or anything like that. You just have to know the description of this table or the of this structure. So as we are approaching the conclusion of this unit, is that there is chemical reaction that makes and breaks the chemical bonds. So the chemical bonds, they are broken into pieces by chemical reaction, and those chemical reactions also make those chemical bonds. So chemical reactions or chemical bonds. Okay. Or chemical bonds, they are made by chemical reactions. So this chemical bonds, they got broken into pieces, and also they got to make up by chemical reactions. So chemical reactions are the making and the breaking of chemical bonds. The starting molecules of a chemical reaction are called reactants. Reactants will be the starting of molecules of a chemical reaction, and the end molecule of chemical reactions are called the products. So this is just self-explanatory that there's a start products, or there's a building up of a product, or there's a make of a product, and there is a product. There's a final product which is kind of like made. So the terminology for such is that chemical reactions, which are the ones that are that forms chemical bonds, are the making and breaking of chemical bonds. That's what chemical reactions are. So sometimes they may not necessarily ask you to describe what chemical reactions are. They might ask you how to describe the chemical bonds, or they may just ask you how are the chemical bonds formed. Then you might have to describe that they are formed through chemical reactions. How do they, you can explain further, is that the starting of the molecule of a chemical reaction, which makes the chemical bonds, are called reactants. And the end products or the final product of those molecules in a chemical reaction that are formed, that form chemical bonds, are called products. Sometimes they may actually say it's called chemical products. You don't have to be confused by that. It's still the same thing. Sometimes they can say chemical reactants. It's still the same thing. You don't have to feel like they are talking about something else, because I've seen in a recent manner where, because terminologies are very significant, especially in this chapter. Ooh, okay, you cannot see my screen. Shares on my side that my device is not fully protected. So I've seen, most of the time where, especially in this unit where terminology is key, where you know that if you talk about something which is slightly different, if you said maybe you're talking about bonds and you're saying chemical bonds, so but you just somebody still come and say bonds. So you don't have to assume that it's the same thing or they're talking about something. So if somebody talk about chemical bonds, it's a whole different thing. But if just somebody is just mentioning bonds only, it's a whole different things as well. But here, if they are saying describe what say chemical bonds or chemical reactants, just know that they are describing this very same one. And here is just a illustration of how they form these chemical bonds of the chemical reactions. So the reaction here is that there is a reactants. We did talk about, if for you to you know what they can do sometimes? They can, I've seen this in one of your past question paper, but the paper that I saw, it was old one, around like 2012, like 10 years back. So they may give you any question. When they give you any question, they just say describe out of this equation, what are reactants? What are reactants? What are the products? What is the chemical bonds? And then you're gonna have to describe. Am I making sense? Just show by thumb if you are following. Or have I been talking for quite a while by myself?
You're making sense, sir.
Okay, cool thing. So, so they might actually give, or they might just give you a final product reaction. Say, break it down. How did they how did they come out with this? Where you get like here, where you get two H2 and O2, which is oxygen, which are the reactions and the chemical reaction. The chemical reaction it's what happened. Chemical reactions is the making and the breaking, yeah. But in simplicity, it's what happened. Or it's you're cooking. It's what you cook. So when you cook, you can cook. I'm just making this in simple form. You can cook, and the products that happen is that you made something or you break something. So you can cook something and come up with one particular thing, or you can cook something and you come with two particular products. So you can cook one particular one formula. That's what they mean by the saying there is the breaking or the making of product. So when they say breaking, it's just necessarily it's not meaning like it's something which is lost or anything like that. So the reactions can be reactions where you can form or make, where you can find that you've got two or more molecules, and then the reaction product or the end product, you find that you have less than those that you started with. So, and then here is the end product where you find that you've got water. How do you come out with the making of H2O from the oxygen and hydrogen, which are the reactants. What are the reactants? The starting of the molecule, or the beginning, or the start point. The final products is called the product, or the chemical product. So also photosynthesis, so we all know what photosynthesis is, but photosynthesis is an important chemical reaction where it is formulated, or it's from the product of the sunlight power, which is the conversion of carbon dioxide and water to glucose and oxygen. This is the formula which form that or break that of that chemical reaction, where you got carbon dioxide plus water, where you find that you got C6H12O6 and plus 6O2. Remember, we once talked about uh, what am I looking for? We talked about the Van der Waals interactions, that they are not evenly distributed. So you might actually have to have that in mind when you're working with this formula, or when you're working with these reactions, because sometimes they may give you a reaction like this and say, describe what interaction is this? Is this an Van der Waal interaction? And you might have to actually look at this and check if it's evenly distributed, and you have to check what kind of reaction is this, and you're going to have to deduce which one are the end products, which one is the chemical, which one are the covalent bonds, and how which one are the products. Is this a chemical reaction? What are the reactants? What are the final products? And you're going to have to describe that. But this is a process of photosynthesis. Sometimes they can just say, describe the process of photosynthesis and how the sunlight conveys the power of carbon dioxide and water into glucose and oxygen in a form of formula. and then you might have to describe this. So it's very, very significant that you know these formulas and how they are made about and what this means. So sometimes this is just a carbon dioxide, and this is water, and this is glucose. This is a formula or the structure, but this formula, the correct term is the formula for glucose and this for oxygen. And then you can see that this reaction, the whole of it is balanced. And then there's the structure of the leaf bubbles for oxygen. You don't need to worry about that. And again, another chemical reaction is that all chemical reactions are reversible. Reversible, that I will explain by that product of the forward reaction becomes reactants for the reverse reaction. And the two opposite headed arrows indicate that the reaction is reversible. So what they mean by that is that this you can also formulate where it comes from, or you can deduce it. So the main point here, or the main thing that you're gonna have to worry about most to the explanation, is the fact that you this errors, two double errors, the one which is forward and the one which is backwards, or the one which is reverse, is just an indication that this is a reversible reaction. All chemical reactions are reversible. The products of the forward reaction become reactants for the reverse reaction. So what is happening here is you're gonna need to, when you wanna describe the terminology, or when you wanna describe the concept, you're gonna have to pay attention to terminology, because they're saying the products of a forward reaction become the reactant. What are the reactants? Reactants are the, talked about this here. Reactants are the starting of molecules in a chemical reactions. So, and here they are saying, this is why I don't like working on a PDF. Here they are saying the products of the forward reactions now becomes the products of the reverse reaction. So, which just in a simple terms, that the ones which were on the front are the ones that have to come back on the back one. But it's not just the fact that you can only just move them and say it have to be formidable, or it have to be formed, or it has to make sense. So that if, for example, here you're saying hydrogen plus nitrogen, it gives you ammonia. So this hydrogen, you can see here in terms of description, H2 plus N, it has to give you NH3. So you will find that this here you've got two N and 3 hydrogen, and the balancing of the equation. And if you can break this final product here, you can actually derive it and break it down to 2H2, 3H2, A plus N on this. So it doesn't just necessarily have to be just a reaction where you can just form it without being able to reverse it into a tabulated formula, into a tabulated reaction that can make sense. It's not just something that you can just say because it's H2 plus 2N3, you can just put 2NH3. No. You actually have to have a breaking down of how this reaction was formed. That's why we talk here at the description here when they said what they said. So that's what they say, the chemical reactions are the making and the breaking. That's of chemical bonds. That's where this is coming from. That you can also break when we talk about, I mentioned before that when we talk about when they're talking about the breaking of reaction of chemical bonds, they're not making is necessarily saying some the reaction will be lost or anything like that. It is talking in an actual fact about the fact that it have to be reversible. You have to, whatever that you're making, make sure that if things go wrong, you can reverse it back. That's just the simplicity of it. So chemical equilibrium. So equilibrium, what is an equilibrium? Maybe if we can just pause here, just to stop you guys to have a question. What is an equilibrium? Just your general understanding of equilibrium. You know what? The slides really describe what it is. You can type if you want. Can I look at the charts and equilibrium? So equilibrium is it's I don't buy the fact that you no one know what an equilibrium is. I'm assuming that all of you are somehow said. So equilibrium is just a striking balance. When we talk about if it's mostly in chemistry, when we say the reaction has reached an equilibrium, we're talking about that a reaction has reached a point of balance. So generally, when we talk about equilibrium, if we're talking, if we are using it in everyday language, okay, the guys will understand this. Sorry, ladies. If we said the match now has reached an equilibrium, we're talking about that it's almost 90 minutes on the game. Manchester City or Real Madrid players now, all of them are equally tired. They cannot press more, they cannot exert more energy than each other. So if we reach in terms of anybody, did somebody who unmuted themselves? Yeah. Yeah. So when we're talking about a general equilibrium, we're talking about if there is that constant point where you cannot go below or you cannot go higher. So things are moving now at a, I don't want to use the physics example, because if we talking about physics, we're talking about the constant now, constant speed. But it's also is similar to that when you say the reaction has reached a balance. It's a balance where you cannot go below or above. You reach a point where all the products or what you are facing or what your reaction it's similar or you're going through at the same pace. So hence here they are saying chemical equilibrium. So hold up a minute. They're saying chemical equilibrium it's reached. Why do they say it's reached, not say is? Because equilibrium is a balance, it's a state of balance, it's a state or it's a state of adjustment between, I'm looking at some notes here, between opposing and divergent influences or elements, where the condition can no longer influences each other, or the conditions can no longer forces a weight on the other reaction, or forces a weight on the other position, but there is a striking balance between those reaction. So here, the reason why they will say it's reached is because they reach a point. It's reaching a point. Go to a certain point because the reaction is moving. The reaction is moving. The reaction is being made. The reaction is being broken, but it will have to reach a point. So it can reach a point of chemical equilibrium when the forward and reverse equilibrium react or occurs at the same rate. Yeah, the example that I wanted to give, it makes sense, of the same speed or the same rate. At equilibrium, the relative concentration of reactants and products do not change. So there will have to be a point where the starting points and the final products, they do not change. They happen at the same time. But for the benefit of your answering, you just need to know that it's a point where in a chemical reaction where the forward and the reverse reaction occur at the same time. Why am I saying in the chemical reaction? Because sometimes your examiner when he describe in your exam, he will describe it as a point in a chemical reaction where the forward reaction and the reverse reaction occur at the same rate or at the same time or at the same speed. Or you may use the fact that the reactants and the products occurs at the same time. Just know that he's describing the chemical equilibrium. So this is just another materials that you can find. It's just a unit of a book where it was come or tabulated from, where your notes were gotten from. The role of chemistry in biology by Dr. Jones in his lab, and you don't need to worry more about this. Not all about this. Little fella here. So reactants and products. This is also a chemical reaction where this carbon dioxide, water, and sunlight. What is this process of? Anyone? It looked really similar to.
The process is photosynthesis.
Thank you. Yes. Photosynthesis. We talked about this, and then we talk of also about the protons. This is what they mean if you wanna describe what in an electrons, what are protons, or in an element, what are protons, which are they're positively charged, the neutrons, no charge, and there are electrons, which are negatively charged, and there's an atom, and then there's a nucleus. And you're gonna have to, when they give you an element, where you're gonna have to know when they're giving you those numbers, and when you're trying to describe. Go back. Sorry. And there's a single covalent bond and a double covalent bond. We're still gonna talk about what are those, and then so what we call ionic bond, and where there's a electron transfer from of ions, and then there is a you know that the formation of, we talked about this in the form of ionic bond, where the formation of a table salt. We're talking about sodium and chlorine, and then there are sodium ion and chlorine ions from the ionic bond there, where you see when you have to see the positive and the negative, which distribute or they describe the ionic bondation or ionic bonds. And don't worry about that. Don't need to worry about that. And that's it in this unit. Any question before we proceed? And we talk about plagiarism. These are not my notes. These are notes which are the presentations by Nicole Tenbridge and Catherine Fitzpatrick, which are mostly the derivation from the biological global approach element, which most of it are from the book by Campbell and others. So we are going to be talking about the chemistry part of the water. So biology is the combination. Even a discipline of chemistry. There's a combination of it with biology, and actually chemistry is part of biology. And or others may say biology is part of chemistry, but all these disciplines are in the under the discipline or under the umbrella ship of natural science or biological sciences. So the molecule that supports all life it's what makes it possible on Earth. It's water. So water it's the basic a necessity. It's a basic resource. Like if you listen to the news, I don't know where most of you come from, but we come from deep rural areas where there's a huge problem of water, where the water is scarcity. Scarce. What everything comes out of water. Even electricity that we're talking about is coming out of water. The electricity today in our country, we are struggling with. I don't need to tell you, some of you are not attending here. Most of you are not attending these sessions because of load shedding, or most of you are not attending with an access that you would rather have because of process of power or blackouts or whatever that you want to call it. But trust me, even energy comes from water. And I know I've been to places where it's a obviously Miss Sumaya she mentioned that she's in Draston. What do you call it, Drastenberg? I'm assuming she's on a holiday, but I once worked in a nature reserve where we're doing field collection, biological field trip in a class. I was doing my second year, where it's a nature reserve, so they have a retreat for where students can come and collect the data, where you can do the practical work, where you can do try to go and collect the mouse, the rats in the field, where you can collect and do the more physiobiological thermotemperature and measurements for all the animal. You can go try to do the traps. You can even go to do some hand collection of bats or birds as well. So they do have what you call a sort of like a retreat. So they didn't use they didn't depend on ESCOM for power. They have what they call hydroelectricity. And hydroelectricity they use in you just need to have a lot of water, and you need to have a cliff where they will go and take power from those cliffs. So what am I trying to say here? I'm trying to say that water is the basic and is what supports life. Life starts at water. Life it begins at water. So water is what makes life possible. And I'm sure you guys can agree with me. So water is only common substance to exist in the natural environment in all three physical states. Those physical states are in a solid form, in a liquid form, and in a gaseous form, in a gas form. So water unique emergent properties help to make the earth suitable for life. The structure of water molecules allow it to interact with other molecules. We talk about that these three forms of physical states, and the structure of those molecules is the one that allows it to interact with other molecules. It's just a form of the illustration of it, the water molecule. And this is the just black belly moth, which are threatened by climate change. We talk we at the beginning of the first session we talked that the most common problem that science is trying to solve is climate change. Climate change is that things are changing. We need to have preservation. We need to think about the future. We need to think about tomorrow. We need to, and it does not necessarily mean that we are we are being ignorant of anything, but things change, and you need to be able to adapt to changes. We talk about with evolution that climatic factors or climatic change affect us. That have an influence in the survival of certain species, in the survival of certain, it may be plant species or animal species, or it may be mammals, or in this case, these birds. And if they don't find the formation or the mechanism to survive or mechanisms to adapt, they may be threatened and they may go extinct or they may be under threat. So you need to go to, there's a page at red list species where you can just type the name. If you can just type the name of this species, they will tell you, sorry, they will tell you how many they are according to scientists, although they cannot have the same exact number. But for sure, the exact number that they will give you is the number of species which are the, I'm sorry, they can give you the number of the exact species which have been identified up to so far, but they cannot just tell you the number of individual, but they can estimate. But they can tell you for sure that they are under three, because maybe the trees that they feed on or the fruits that they feed on, each tree is no longer available, it's been wiped by whatever and whatever, or the type of environment that they prefer is been wiped off because of disturbance. We talk about the disturbance, that there's a natural disturbance and a man-made disturbance, where a natural disturbance we could be like there was a fire, and for some reason, because the rain didn't rain for the past the amount of rainfall for the past 2 years or 5 years has been less than it used to be, and then the rejuvenation of that biodiversity or that vegetation is null. It cannot recover, it cannot be recovered to an original state. Therefore, these fellows no longer have what we would term a home or what we would term a vegetation to lay their heads at. Or sometimes you can find that their vegetation which they used to prefer, there's now a big establishment which is being established there, and then they are no longer phased out and they have to be wiped out. Proceeding into that is that this concept of polar covalent bonds in water molecules, which results in hydrogen bonding. So in the water molecule, the electrons of the polar covalent bonds spend more time near the oxygen than the hydrogen. We'll explain later what they mean by that. So water molecule is that for a polar molecule, and the overall charge is unevenly distributed. So it's not equally distributed. Just like what? Just like Van der Waals interaction. Talk about that previously. And the polarity allows water molecule to form hydrogen bonds with each other. So those the polarity will be the determining factor which will force the thank you, which will force the water molecules to form hydrogen bonds with each other. So in these water molecules, where the electrons of the polar bonds spend more time near the oxygen than the hydrogen. We'll explain why, because sometimes they may say, why do the water molecules in the electrons of the polar covalent band spend more time in the oxygen, not in there, but near the oxygen rather than in the hydrogen? And then you might have to explain why is that. 5 months, and you have to explain. So it may come like that, where sometimes the water molecule is that, well, because it's a polar molecule, where the overall charges within those water molecules are not equally distributed or unevenly distributed, because the polarity of those water molecules to form hydrogen bonds with each other. So here is another structure where you find the region of partial negative charge, and then you find the hydrogen bond where there's a positive, not positively, and then you find the polar covalent bond, and they talk most that they prefer to be near near oxygen than in the hydrogen. where you can even check here that there are more. And with that results, what does it result? It results in an unevenly distributed charge because there's a preference. These fellows here, they prefer to spend more time near the oxygen than the hydrogen bond. So 4 emergence properties of water contribute to S sustainability for life. We talked about sustainability. What is sustainability as a general term? Most of you look like you sound like people who listen to news. In the news, you will hear them say, we need to have sustainable energy plan. Our energy needs to be sustainable. In the news, the minister will be like, we need to formulate the plan which, or the production or the generation of energy will have to be sustainable. But sustainability is just as it as it as it's a term by itself, being able to reimage or reproduce or recover, for the lack of a better term, and be able to survive and stand. So the sustainability of life, the sustainability of life on Earth, it's resulted in 4 emergent properties of water which is contributed. So 4 properties that facilitate an environment for life are the cohesive behavior, ability to moderate temperature, expansion upon freezing, versatility as an insolvent. So when we talk about sustainability, we're talking about the fact that uh, you're gonna have to sustain. Life has to be sustained, and the properties to sustain that environment, it relies on cohesive behavior form or ability to moderate temperature form, expansion upon freezing, and versatility as a solvent. So you will have to also look out for this and be on a lookout for when they request you to describe what are the four properties which are properties that facilitate the environments for life, where you're gonna have to describe the cohesive behavior, ability to moderate temperature. Moderating temperature is more or less like the equilibrium. Not equilibrium, I'm wrong, but ability to moderate temperature. Being, for example, today is the weather was a bit chilly when I woke up. So in order to moderate my temperature, so that my temperature, because temperature were very cold, I had to wear a jersey. So we as human beings, we can be able to for example, we can wear jersey, we can wear the type of clothes that they will need to moderate our temperature or go hand in hand with other reptiles like a lizard. When the temperatures are cold, if you go to mountainous areas, you'll find that if you are climbing or you are doing what do you call it, hiking, whatever, then if you are lucky, early in the morning, around this time in the winter, you might find them doing what you call basking there in the sun when they're getting the more temperatures, because the temperatures are very low. So they have to regulate and moderate that temperature. So you're gonna have to have that ability to moderate your temperature and expansion upon freezing. So cohesion of water molecules. Collectively, hydrogen bonds hold water molecules together. How? That's a phenomenon called cohesion. The cohesion is hydrogen bonds hold water molecules together when things. So cohesion in politics, they will say the center is a holding when there is holding of together when the hydrogen bonds hold water molecules together and they are able to stand on their own. It's called cohesion. So what does this cohesion do? The function of a cohesion, it helps transport the water against gravity in plants. So they might request you to describe what is cohesion and also describe with an aid of an example. Then there's also an adhesion, excuse me, adhesion, which is an attraction between different substances. For example, water, between water and a plant. So the cohesion is the phenomenon which describes the process where hydrogen bonds hold water molecules together. But contrary, adhesion is an attraction between different substances. So cohesion is only in water. Adhesion is between other different substances. So between water and the plant. So cohesion is in water, within water itself, but adhesion is between water and the plant. So cohesion helps make sure that transport water against gravity, but this one is between water and the plant and cells. So here is the illustration where they are just describing here. If you can just look here in the structure of this tree, where you're gonna see the evaporation pulls out water upward. That's the process of evaporation. We know that. And the types of water that is conduction in the cell, with the process of adhesion, and then there's a process of cohesion. What is cohesion? Where the hydrogen bonds hold water together, water in water molecules together, and helps so that the water against the plants of the gravity of the plants. And here is the direction of the water movement when it's being taken up by what? By evaporation. Then the cohesion helps the water against the gravity of the plants. And then there's an adhesion, which is the attraction between substances between water and the plant cell walls. Excuse me. Then two types of water conducting cells. We're gonna go there. What is that? No comment, no. And then you will see the animation of water transport in plants, where the water is being transported from the leaves, and then it's transported from the branch, and then it's being transported from the root cells as it goes. And there is what we termed surface tension. Hold up a second. Thank you. So surface tension is a measure of how difficult it is to break the surface of a liquid because unusually the high surface of water tension due to hydrogen bonding between molecules, the molecule at the air-water interface and the water table. So water has this this unusually high surface tension. And why is this surface tension? What is surface tension? The measure of how difficult it is to break the surface of a liquid. So therefore, water has this unusually measure of difficulties in being able to break the surface of a liquid due to the hydrogen bonding between the molecules at the air-water interface and to the water which is below. So, like for instance, here you can see this little fella. This what's this again? Why am I losing the name of this? The spider from which spider come from the family of? The Lepidoptera? No, it's not from Lepidoptera. We'll find out that later. Then the moderation of temperature by water, moderation. We talked about this. If you remember here, we talked about uh, four properties that facilitate the environment for life. Where we're talking about the cohesion, behavior, ability to moderate temperature, expansion upon freezing, and the versatility as a solvent. Then where we are, we're talking about the moderation of temperature by water. So water absorbs heat from the warmer air and releases store heat to cooler air. So what they're saying is that these water molecules, like for instance, if there's a sunlight on any usual day in a water body or in a wetland or in a stream, let's not even go there for the dams, big dams or anything. Let's use the streams, which is like a water body or a wetland, where the water absorbs heat from warmer air or warmer temperature and releases the stored heat to cooler air. So they will absorb the heat and releases the stored heat to cooler air. And they can also absorb or release the large amount of heat with only a slight change in its own temperature. So their own temperature can re, 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 not rapidly, but rarely be affected if they can absorb or release large amount of heat with only a slight change that can impact its own temperature. Therefore, in terms of temperature and heat, these are the terminology you need to pay attention to. That's kinetic energy, which is the energy of motion. The kinetic energy associated with the random motion of atoms or molecule is called thermal energy. Temperature represents the average kinetic energy of the molecules in a body of a matter. And thermal energy that is transferred from one body of of a matter to another is defined as heat. So I will expect you guys to when you get into your test or in your exam room or whatever, to have the description or the knowledge of what kinetic energy is, which is simply just the energy which is in motion, or the energy which is sometimes there are description which talks about the energy which is being transferred. That you wouldn't be entirely wrong on that one. And this kinetic energy, they are associated with random motion of atoms or molecules, which is called thermal energy. And this temperature in the thermal energy represents the average kinetic energy of molecules in a matter of in a body of a matter. So we're also gonna talk and remind you. I know we talked about this last week about what is matter, of the thermal energy in a transfer from one body of matter to another is defined as a heat. So the different or the tricky part here is that you must not confuse if they say the transfer of energy, that you might think that they're talking about kinetic energy, but the transfer of energy from one body of a matter to another, it's a heat. It's a heat energy. But the transfer of energy, just the transfer of energy, or the energy in motion. Hence, your lecturer here used the terminology, the transfer of energy of motion is it's kinetic energy, so that there won't be any distinctive confusion there, where you find that you are are not in a very, you are trapped in a very good confusion where you might find that you are describing one thing, or you find that the other thing of sound really eerily similar to the next. Then a calorie, which is a unit which is described by unit cal, is the amount of heat which is required to raise a temperature from 1 gram of water by 1 degrees. So it is also the amount of heat which is released when 1 gram of water cools by 1 degrees also. So calories on the food packages are actually kilocalories, and you don't have to worry much about these units. 1 kilocalories is equal to 1,000 cal, because a calorie, this unit, is the amount of heat which is required to raise a temperature. So the amount of, what is heat? Heat is the transfer of energy from one body of matter to another, the transfer of energy from one body to another, the transfer of it. So the calorie is the amount of heat which is required to raise a temperature. How much of heat will you need to raise a temperature in a gram per unit, which is proportionally to temperature, or to a degrees temperature. So in this scenario, or the formula for cal is that the amount of heat which is going to be X amount, but is going to be a constant value by 1 gram of water by 1 degree temperature. And it also absorbs heat. It absorbs amount of heat released when 1 gram of 1 gram of water cools by. So they also absorb, it also absorbs the temperature with 1 gram of water by one temperature, one degree Celsius, and also when it releases using the same amount, or the same formula of 1 gram of water, which is cooled by 1 degree temperature. So here, the other thing, what they are showing you, that on food packages, that's could be not a fun fact, but it's an actual fact, that kilocalories, kcal, is equal to 1 kcal. It's equal to 1 calorie. It's equal to 1,000 amount of heat which is required. So the amount of heat which is required in 1 cal, it's actually 1,000. In 1 kilocalorie, it's actually 1,000. The joule is another unit of energy, where 1 joule of 0.239 cal, or 1 cal, is equal to 4.184. You don't need to worry about the formulas of how they calculated when it comes to that. And I don't really think that your examiner will ask you to do calculations with that regard. Then what are high specific heat? The specific heat of a substance is the amount of heat that must be absorbed or lost for a 1 gram of that substance to change its temperature by 1 degree Celsius. What amount? So your examiner might say, give the amounts, how to determine these amounts of a calorie, of kilocalories, or of a joule, and sometimes we will even go further to say this of the specific heat. So when you're going to have to describe that the specific heat of a substance is the amount of the heat that must be absorbed or lost for a 1 gram of that substance, is to change it. How do you change by how much? By 1 degrees Celsius. The specific heat water is 1 calorie per gram. That's the formula. And the water resistant changing its temperature because of its high specific heat. So there's resistance changing of the temperature of water is due to the fact to the substance, to the amount of heat that must be absorbed or lost for 1 gram of that substance to change its temperature. And remember that the heat is the thermal energy in the transfer from one body to another. So that's if when you're going through all of this, because the main aim here is to check the amount of heat which is needed. So when you're going through all of those, when you are requiring them, you should have the description of what heat is, or the definition of heat at the back of your hand or at the back of your mind at all material times. Then water high specific heat can be traced to hydrogen bonding. Why? Because heat is absorbed when hydrogen bonds break. Heat is released when hydrogen bonds form. So if you remember here, we talked about the fact that calorie is the amount of water that is required to raise or build amount. But when you talk about the amount of heat which is released by 1 gram of water when it cools by 1 degree Celsius. So water's high specific heat can be traced to hydrogen bonding. Then when I ask you that and so why is that, you're gonna have to tell them that because the absorption of heat when hydrogen bonds break, and the heat is released when the hydrogen bonds are being formed. High specific heat of water minimize the temperature fluctuation to within limits that permits to life. And just another animation of another Pacific Sea ocean, which you don't need to worry about. Then evaporative cooling. Evaporative cooling my notes are still visible, yes. Is the transformation of a substance from liquid to gas. Remember, you need to have this mind, or what we're talking about here is we are here. If I can indulge with you, we are talking about the 4 things. Remember those 4 things? We're talking about the 4 properties that facilitate an environment for life, which are cohesive behavior, ability to moderate temperature, and the expansion upon freezing, and versatility as solvent. So you're gonna have to have that in mind when you got to have a cohesion, if we may put our biology language there, where you're gonna have to put your thoughts into put, or the evaporation cooling. Evaporation, you know what evaporation is, or vaporization is the transformation of a substance from liquid to gas. Substance from liquid to gas. We talk about that the water is in the 3-stage form, that it can be in a gaseous form, it can be in a liquid form, and it can be in a solid form. So heat of vaporization or heat of evaporation is the heat a liquid must absorb for 1 gram to be converted to gas. So when you're doing that reaction, that formula will stand out from the fact that you are measuring the amount of heat a liquid must absorb for a 1 gram in order to be converted to gas state. So as a liquid evaporates, its remaining surface cools, and the process is called evaporative cooling. And evaporative cooling of water helps to stabilize temperature in an organism and the bodies of water. So this cooling evaporative cooling also has a function of stabilizing the temperatures in organisms and bodies of those water. Floating of ice on a liquid water, which is another good explanation there, which you might look out for, is ice float in liquid water. Why? Because hydrogen bonds in ice are more ordered, making ice less dense than the water. That's the explanation. So this is not just now an explanation for your examiner. This is also an explanation also to people when they ask you, you did science, tell us why, if these two objects are both water, but the other one can have more weight than the other. So the ice floats in liquid water because their covalently hydrogen bonds in the ice are more ordered. They're in a more ordered form, and it makes them less. It makes their density much lesser than the one of a liquid form. So water reaches its great density at 4 degrees Celsius. Ice sink, all bodies of water will eventually freeze solid and making it impossible for life on Earth. So that's the striking balance, or that's the sustainability, or that's so water reaches its greatest density at 4 degrees Celsius, making it permissible that it does not eventually sink. Because if it sank, or of all ice sank, all water bodies will eventually freeze to solid and will be in a solid state where it will not be unbearable. It will be very unbearable. And this is just a illustration or animation of ice, which are hydrogen bonds where they are stable, and then liquid ice where hydrogen bonds break to and reform at this point. Then many scientists we talk about this when we talk about climate change, global warming. They are worried about that because they have a profound effect on icy environment around the globe, and the rate at which glaciers and Antarctic ice are disappearing poses the extreme challenge to animals that depend on ice for their survival. So even the areas where their temperatures are extreme, they are being disturbed, or they're being altered, or because sometimes desert, when we talk about desert or we think about desert, we only think about desert of a brown ice or Namib desert, and it's also when you can be a desert when it's a pure ice form of a vegetation with just a pure ice form without any other. So because sunlight is important also for the growth of organism, for photosynthesis, and for the generation of food for plants species. So here's another illustration where it was the sea ice, which was captured in 2014, and then the sea ice. Okay, I don't know if you're gonna be able to see that. The sea ice, which is lost from September 1979 to 2014, which is just this is just an illustration of how the loss of ice for individuals such as this fellas here, polar bears, and some species which feed on something there, and some fish species are lost if, or they are disturbed if there is a loss. This ice is lost in the sea in this kind of formation. So there are also benefits from loss of ice, where we talk about if you can see phyto or plankton, we'll see bowheads, whales, These are just the structures and the extent to which the sea in September, I see in September 2014, it's now at, compared to the extent of sea in September 1979. And this is just a North Pole. Don't have to worry about but there are temperatures. That's where you just have to be grateful that whatever that we may be going through as a continent, but we do have good temperatures where they are very bearable. And then you see this Pacific walrus and Alaskas, which are just here home by the. So these are the species or the individuals which are harmed or which are affected negatively by the loss of ice, which is pretty much bad. So water is the last one of the four properties of sustainability which the life have or which the life forms. And what are the solvent of life? A solution is a liquid that is completely homogeneous mixture of a substance. And the solvent is the dissolving agent of a solution, and the solute is the substance that is dissolved. And an aqueous solution is the one in which water is solvent. So here there's no need for me to just explain anything. You just have to make sure that you don't get into an exam room, ladies and gentlemen, without knowing what these are, because from this, your examiner might just request you to just describe or differentiate between the solvent and the solution, or the aqueous solution, or you can just say describe what solution is with also the help with an example of solvent, solute, and aqueous solution. Or this also an example. We're talking about sodium chloride, where the final product finally be there or in a solution. How this reaction will have to end up in a solution where in which one water is solvent, or how is this solute? So will it be insoluble, or will it be solute, or will it be solvent in this form or in another? So water is versatile solvent due to its polarity. So they will ask you, why is water versatile solvent? You're gonna have to tell them that it's because due to polarity, and when ionic compounds dissolve in water, each ion is surrounded by a sphere of water molecules, which are called hydrogen shells. I think we did touch a bit last week about the hydrogen shell, if it's not the week before. So this hydrogen cell, hydration cell, not hydrogen, but hydration cell, it's when ionic compound dissolve in water, and each of them are surrounded by a sphere of this water molecule. And water can also dissolve compounds made of non-ionic polar molecules. So it's not only on ionic polar molecules only which can help or which can make the water to dissolve into compounds, and even large polar molecules such as proteins can dissolve in water if they have ionic and polar regions. And it's just an illustration of that. And hydrophilic and hydrophobic substances. I saw this, I'm sure, in your tutorial letters, in those assignments. There's this question, which yeah, this the one question. If I didn't see it there, then I saw it somewhere else. But I can tell you for sure that I saw it somewhere. So this also goes without saying that you're gonna have to know more about this hydrophilic and hydrophobic substances, where hydrophilic substance is one that has an affinity for water, and hydrophobic, not hydrophobic. It's the substance is the one that does not have an affinity to water. I'm opening my other notes here because I need to check. We'll focus on it when we go further about the affinity. So all molecules are hydrophobic because they have relatively non-polar bonds, and hydrophobic molecules related to oils are the major ingredients of cell membrane. Then solute concentration in an aqueous solution. Most of them are reaction in organisms which involve solute that are dissolved in water. And when carrying out experiments, they use mass or weight to calculate the number of solute molecules in an aqueous solution. So they in order to check the number of solute in the molecules in an aqueous solution, they use the M, or as a mass or weight, to calculate the number of those solute molecules in an aqueous solution. So molecular mass, I remember we talked about the fact that we're going to go to the description of this last time. I think we were talking about earlier in this session. So molecular mass is the sum of all masses of all atoms in a molecule. We'll come to that. The number of molecules are usually measured in moles, where 1 mole is 6 times 23 cubic squares molecules. And this is an Avogadro's number, and the unit Dalton, where they are defined such as that 6 times 10 Daltons is equal to 1 gram of this molecule. You don't need to worry more about this formula, but what you need to worry more is the fact that this molecular mass is the sum of all these atoms in a molecule. And molarity is the number of moles of a solid per liter of a solution. And the unit for molarity is M. And the unit for molar these are for moles is mole. And the unit for molar mass is M. If I'm mentioning it correctly. So no, the unit for molarity is M, and the unit for moles is mole, M-O. Small, and it's small caps, M-O, because the unit is very, very, very important. So as we go further, what does this explain? What does this represent? What does this give? What is the point of all of this? What does this represent? This represents the possible evolution of life on other planets. Biologists are seeking on other planets to have a concentrated their search on the planets. Then in our solar system, Mars has been found to have water, and more than 800 planets has been found outside of our solar system. There is an evidence to, you don't need to worry about this, but what they are trying to show here, or what your lecturer is trying to show you here, that water is very, very significant, and it's a significant state in which you need to familiarize yourself with. Before I proceed, any question up to so far? So acidic and basic condition affect living organisms, and hydrogen atom in a hydrogen bond between the two water molecule can shift from one to the other. Yeah. And the hydrogen atom leaves its electron behind and is transferred as a proton. We talk about what protons are and what electrons are, what neutrons are in a previous slides. You're going to have to refer to those in the first unit. And the molecule that lost the protons is now a hydroxide ion. Then there's a hydrogen ion, or as a proton, the hydrogen leaves its electron behind and is transferred as a proton. And the molecule that lost protons is now a hydroxide ion, but the unit is OH, and the slash negative on the top right there. But on the hydrogen ion, it's a H, unit is H plus a unit of a hydrogen plus on the top right. The molecule with extra proton is now a hydrogen ion with H3O, though it is often represented as H, but you can describe it as H. So the molecule that has an extra proton. And water is a state of dynamic equilibrium in which water molecules dissociate at the same rate at which they are being reformed. So whenever you see this equilibrium, the word equilibrium, you need to know that in that reaction or in that formula, whatever that they're happening, you're probably going to find the same rate. So if your examiner is asking you a question which has equilibrium on it, usually you might write a paragraph or anything like that, but you will find that the key words that they're looking for in your answer, the key descriptive words will be the same rate or at the same state or same. They have to be the same. So that's why here we talk about that water molecule dissociate when they're that process of the associating. How does it happen? It happens at the same rate at which they are being reformed again. We talk about the if you remember, we talk also about the reversible reaction, that the reaction have to be reversible in that form, that the end products, the products can be at the same form with the reactants when they start the reaction. And it's just a information here. We'll talk about the water which is being dissociated at the same rate. So, and we mentioned that if you see this in a reaction where there is a forward arrow and a reverse arrow, it means that this reaction is reversible. Are you getting that? Anyone? Just show by some. Cool. See one some. The others are sleeping. Thank you. And the hydrogen ion. Then, through statistically rare, the dissociation of these water molecules has a great effect on organisms. So there are benefits where the changes in this concentration of hydrogen. What is this? We talked about this. We're talking about hydrogen ion and hydroxide ion. We talk about the hydrogen ion and the hydroxide ion can drastically affect the chemistry of a cell. And concentration of this hydrogen ion and hydrogen oxide are equal in pure water. The adding of certain solutes called acid and bases modify the concentration of this. What are these? I'm losing its terminology. Hydroxide ion and hydrogen ion, hydroxide ion and hydrogen ion, which you need to know very well. So the adding of this solute called this acid, they have modifying the concentration of these two ions. And so therefore the biologists use the pH scale to dissolve whether a solution is acidic or basic, which is the opposite of acidic to one of those. So acids and bases. Then acid is a substance that increases the hydrogen ion. Am I correct? It's hydrogen ion, right? Yes. So acid is a substance that increases the hydrogen concentration of a solution. But the base is the substance that reduces the hydrogen ion concentration of a solution. That's the difference. And I'm sure your examiner might require that. So the acid increases the hydrogen ion, but the base reduces the hydrogen ion in a concentration of that solution. Strong acids and bases dissociate completely in water. So weak acids and bases reversibly are in that reversible reaction. They do what? They release and accept back hydrogen ions because it's a reversible reaction, but can still shift the balance of hydrogen or hydroxide ion away from neutrality of those solutions. And the pH scale, if you in any aqueous solution at 25 degrees Celsius, the product of those hydrogen and hydroxide ion is a constant and can be written as follows. And you just need to worry more not about this formula, but the pH solution is defined by the negative logarithm of hydrogen concentration, which is written in a form below. Then the one that you need to worry more about is the for neutrality in an aqueous solution, hydrogen ion is in the form of pH of 7. Here, where you're gonna have to find it like this. But the calculation, you don't need to worry about this calculation. But what you need to worry about is that the neutrality of this aqueous solution in the pH is 7. So acidic solution have pH value of less than 7. This you need to note this, very important. And basic solutions have a pH value greater than 7. Why is this important? Acidic, they have value less than 7. Basic have a value greater than 7 because acid are substance that increases. But the bases are the one that reduces. Hence, the acidic have a value which is less than 7, and basic have solution which is greater than 7. So there is that balance. And most biological fluids have pH values which ranges between 6 to 8. If it's anything less than that, yeah, well, something to work. And if it's anything over 8, a value of 8, it's also something to worry about. So here's just a thing that you can just into what you guys consume and what you guys have. You can just see them. And the pH value here is a scale of 0 to 14. See that how many of you have eaten Coke or have drank Coke? How many of you are going to drink Coke today? And you're in the pH of around 4. And you see here, and all this just a neutral solution. It's a basic solution. This is an acid solution. What is an acid? Let's just go back one more time. Acid is the substance that increases the hydrogen concentration, hydrogen ion concentration. And the base is the substance that reduces the hydrogen ion concentration. And here are the basic solution. The basic are the one that have to be reducing, and the acid are the one that are increasing.